SN2 reactions, why do they undergo inversion? So the reason they undergo inversion is because the necessity to break the bond to a leaving group requires that you put electrons in that sigma bond's antibonding orbital, which is sigma star. So for every bond you have, right? So if you talk about a carbon-bromine bond, who owns the electrons? Well, the bromine probably owns the electrons. So you draw the bonding orbital kind of like this, and that's a sigma bond. The antibonding orbital is where electrons are less likely to be at, and you draw that over here. That's going to be much more prevalent by the carbon. That's where electrons are not at. That's sigma star. And we know that bond, the angle between these two things is actually 180 degrees. And the reason we know that is because when we do an SN2 type reaction, we actually get inversion, where a nucleophile puts electrons into sigma star, and at the same time as you put those electrons in sigma star, the sigma bond breaks. This causes inversion, because what we have now is this, and now we have Br minus over here. Right, so another way to look at this, if you had it in a molecule that was an asymmetric center, right, something like this, right, that's RS, the carbon that has the leaving group on it. When the nucleophile reacts, it of course comes to the back side 180 degrees away. That's where that sigma star is at. And what happens here, it causes inversion. It pushes these things forward. And if it was R, it becomes S. And if it was S, it becomes R. There you go. So you get inversion. Yeah, so this is number 10, 2017 version A. Version A. So whatever's on the bottom of the arrow is the solvent. And I think I literally even wrote in there solvent. It said to make sure people didn't mix it up. So it's polar aprotic solvent. This is a reactive nucleophile, right? K plus Cn minus. It's not very big, right? It's a like that. So it's going to do an SN2. It's going to do an SN2 reaction. So what happens then is going to be inversion. So this is a little different angle to look at than you'd had before. But it's the same idea. Got to go the back side attack, right? All in one step. That's what that means. So the iodide's gone. And the iodide was wedged. So that means the cyanide, the nucleophile, is going to have to be hatched because it's come from the opposite side, Cn. And that means the H, which was hatched, now becomes wedged to get that inversion in this case. Yeah, you could put, if you want to, you could say, just to balance your charges, you have that for sure. Number 5 for version A, looking here, let's ask you to assign all asymmetric centers as RS and assign EZ or neither for all alkenes. So for this one, let's focus in on the alkene. So remember how we do alkenes? We split them in half, right? And then we say, we rank them from either side of the carbon. So from this carbon, it's bound to a nitrogen, it's bound to a carbon. So it has higher priority, nitrogen or carbon? Nitrogen. So this side would have higher priority. Go to the next one. You have a carbon versus a hydrogen here. Right? There's a hydrogen there. So what have higher priority? The carbon. So both highest priorities on the same side. So this would be a Z alkene. And so just don't forget how to do E and Z alkenes. How to split them up and that kind of stuff. In this situation right here, what's stable? This is a carbocation. What's stabilizing this carbocation? Do you know what are the 3 ways to stabilize carbocations? Hyperconjugation. There's 2 types of resonance: pi bond resonance and lone pair resonance. What's going on here? Hyperconjugation. All right, it's just hyperconjugation. How do you know it's hyperconjugation? You look how many bonds away? Look for sigma bonds, 2 bonds away from the carbocation, right? Just same as your beta hydrogens, right? So now we're just looking at sigma bonds. So 1, 2 bonds away. So it has 3 hyperconjugation interactions, but these do not. So it's a primary carbocation. That's part of the reason why it's not very stable, because it only has 1, 2, 3 sigma bonds, 2 bonds away. So the reason why this is stabilized is because of hyperconjugation. Remember, that one doesn't actually move electrons. That just helps stabilize it. Number 11, version A, 2017 test. So the first thing I did was number the carbons. Number your carbons. And it says give the other reactant for an E1 reaction in the box above the arrow. Show the mechanism for an E1 reaction below, including the major product form. So I'm telling you it's an E1 reaction. E1. It literally says it twice. So you should know you're going to make a pi bond. Right? And what kind of reactant do you want in that box if you're going to make a pi bond for an E1 reaction? What do you want? What is E1 like for a base or nucleophile? It like something reactive or unreactive? Unreactive. And then you want it big or small? Big. Elimination likes big things, right? Remember, substitution wants small things. So I just did the terbutanol. I just did this 4-carbon thing. You could have done anything. Methanol is probably not big enough. I would have done something bigger, right? So you wouldn't have earned all the points for that. So I want So that second level, right? You realize it wasn't reactive, but then I want something big if it's E1, right? What's the first step in an E1 reaction or an SM1 reaction? Leaving group leaves. Leaving group leaves. Nice. So what kind of carbocation did we just form? Primary, secondary, tertiary, benzylic, allylic, lone pairs. Secondary. Is that the most stable carbocation we can ever have? No. So what could we do? We could do a rearrangement, or we could do resonance. Can we do resonance right now? No. Can we do a rearrangement? Yes. So remember, for rearrangements, again, we're looking for sigma bonds 2 bonds away, right? So what do you want to rearrange here? What do you want to move? Shift what? Hydrogen on carbon 3. Nice. Make sure you show the electrons in that bond moving over, not the hydrogen, the electrons in the bond. So that's H shift. So now there's a plus charge on which carbon? There should be one on carbon 3. And this is a tertiary carbocation, so we went from secondary, now it's tertiary, and we would think, oh, this is great. But we can make it even better, right? We can make it benzylic, right? Remember, benzylic has all that pi bond resonance, right? So we can do one more shift, right? Resonance beats hyperconjugation, right? Just like we're doing Zaitsev's rule, resonance beats Zaitsev's rule. So we rather do another shift here, where we're going to shift another hydrogen, and this time on carbon 4. So another H shift. Now there's a plus charge on carbon Oops. 5, 4. No, it's a plus charge on carbon 4. Right? Now, is this the most stable carbocation we can have? Yes. Can't get any more stable than this. Can't make it any more stable. Right? Can't make it any more stable than this. We usually don't like to break up benzene rings. So if you want to start, you wouldn't want to do resonance at this point. We don't like to break up benzene rings. All right. So now we're back to, we've made the carbocation as stable as possible. What's the last thing you do for an E1 reaction? You got to find the beta hydrogens. Beta hydrogens. Once you've done all the rearranging and resonance, you find the beta hydrogens. Where are the beta hydrogens at? How many types of beta hydrogens are there here? How many types of beta? Just one. Where's the beta hydrogens at? Carbon 3. Just on 3. 1, 2 bonds away, right? 1, 2 bonds away. The hydrogen's 2 bonds away. So now we finally use that base we picked in the very beginning to do the E1 final step. And what kind of alkene are we going to make? E or Z? What kind of alkene do you think we'll make? E or Z? E. We want a more substitute alkene, right? Things like to be away from each other. Z same side is Z bad. It's Z higher in energy, right? So pick E. So that E alkene. And the other thing we made was that protonated solvent. And of course, chlorine has been along for the ride. So if you wanted to use chlorine to take the H, you could have. More than likely, it's the solvent because there's a lot of it around that balances our charge. So you get the conjugated resonance, right? Notice is resonance now. But a lot of people will miss this step. You need to do that extra shift to go from secondary to tertiary to, this one is secondary, but it's benzylic, right? Keep making more stable carbocations as you go. So how do I make sure it's an E alkene, not a Z? So then you got to know something about how to do alkenes, right? So carbon, that's a tie. This is bonded to 3 hydrogens. This is bonded to a carbon and 2 hydrogens. So this one wins. This has higher priority. And then the other one we have H versus this. Carbon beats H. So they're on the 2 highest priority groups are on opposite sides. So that's an E alkene versus a Z. And we'd rather make E because they're more stable, because the bigger things are away from each other. That's what that means. Okay? You keep on shifting until you can get to the most stable carbocation possible. So like the most stable would be a tertiary benzylic. But right, resonance beats hyperconjugation. Right? So if you can do resonance, you're going to do it. Right? That's why I showed you those 3 things, right? Ways to stabilize carbocations: hyperconjugation, lone pair, pi bond resonance, and lone pair resonance, in that order of importance. So let's say you accidentally drew the Z. All you got to do is just move one of them, flip these positions on the carbon, on the alkene. Just flip them around. Yeah. You want it to be E. Notice how there's no wedges and hatches here, so you're not like restricted. All right, E1, you're not restricted, right? E2, you got that anti-periplanar problem. So here, you're always looking for E1's easy. E1, you're going to go resonance, E alkenes, the whole thing. Zaitsev rules, no problem. So how do you do an SN2 reaction? Let's say I've told you it's going to be an SN2 reaction and a chair conformation. So I show it 2 ways. It can be either axial or equatorial. It doesn't matter for SN2, right? Remember, for E2 it has to be axial, but for SN2 it doesn't matter. The thing you got to remember for SN2 though is that it ends up being so it doesn't matter. So this one doesn't matter, axial or equatorial, but you got to be careful. Like, so notice the chlorine here is, in both cases, it's up, right? See, it's pointed up. So the nucleophile is going to have to come from the opposite side, the back side, right? So the nucleophile will end up on the ring down, right? So if you look at this position on the ring, what's the down position on this ring? It's axial. So when this nucleophile comes in, We know that the nucleophile is going to be on the opposite side of the ring, and it's going to be equatorial because the chlorine has left. See that? On this one, coming from the other side, same deal, SN2, but now the chlorine was equatorial, so the nucleophile is going to end up being down and axial. Right, so it's still inversion. It went to the opposite side, right? So it's just another way of looking at it. So this is from the workshop, quiz 2 workshop we did. So we did something similar in our notes. So essentially, if you were breaking this down, so SN1, SN2, SN1, E1, E2, what type of alkyl halide do we have? We got a secondary. Does that eliminate anybody? Nope. Do we have a reactive nucleophile base? Does it have a negative charge? No. So that eliminates, really makes less likely that SN2 and E2 are happening. Also, if you look at this, just by looking at this, you could eliminate SN2 and E2 because you'd notice a 4-member ring all of a sudden there's a 5-member ring, so there must have been rearrangements. Can rearrangements happen in SN2 or E2? No, right? Because there's no carbocations. You need carbocations to do rearrangements. So it's either SN1 or E1, and which one is it? It's both, because look at the two products. There's both an elimination product and a substitution product, so we got to do both here. So what's the first step in an SN1 or E1 reaction? Leaving group leaves. We, of course, should number our carbons. Six. Secondary carbocation, can we make it more stable? So right, you should all be tipped off, right? 4-member ring, that's pretty unstable. The butanes because of the bond angle strain. So we're going to do a ring opening here, and we look for sigma bonds 2 bonds away. And I'm going to break the bond between 3 and 4. So 4 is now going to be bonded to 2. So I could draw this. So this is an alkyl shift, they call it, right? So I can make it look ugly, make it look pretty. We'll do the ugly version first. Oops. So 1, 2, 3, 4, 5, 6. Where should there be a plus charge? Nope. 4 got a new bond. 4 is now bonded to 2. So 3 should have the plus charge. So let's draw it in a better looking version. One, 2, 3, 6, 5, 4. Right? You with me? So what kind of carbocation is this? This was a secondary. This is also a secondary, but notice how we don't have the former ring, so we got rid of ring strain. Can I make this more stable? Yes. What can I do? Hydrogen shift from where? Carbon 2. All right, so another hydride shift. That's going to give us a tertiary carbocation. And at this point, you can either do elimination or substitution, right? Hopefully, we all can see from here, you can go this way or this way. Since I've already done E1, I'll do the SN1, since I did the E1 before. So I'll show you the SN1. So E1 and SN1 actually have the same exact intermediates, right? They're the same exact intermediates. The only thing that's different is at the very end, do you do an elimination or substitution? So we'll do the substitution one. So the oxygen reacts with the carbon. How many hydrogens bonded to that oxygen right now? 2. How many are going to be bonded after it bonds to that carbon? 2. Did I move? Are there any arrows moving on either of these hydrogens. Stop it. Don't do it. Nothing happened to them. They're still there. If they were carbons, they'd still be there. Don't lose your carbon. Don't lose your carbons or hydrogens. Only thing that happened was oxygen bond to carbon. That's it. So this oxygen now has the plus charge, right? And then the last step would be another water coming, that deprotonation step to take one of the hydrogens. And then that goes to there, right? But you need to show this step. Don't skip steps. Don't let hydrogens fly off. Don't lose carbons. Number stuff. Good.